Okay, so we have another velocity time graph question. This is a request to do with how would a velocity time graph work if we had say, a rocket launching up into the air. So the scenario is rocket launches up into the air. Um, it's going to have a thrust force acting upwards. At some point, it'll run out of fuel, and then sort of what happens from that point. So normally it's going to be like a terminal velocity question basically, but it's sort of in reverse. So we have a rocket that's launched at time zero. Um, the moment that it launches, we have a large resultant upwards force. We effectively just have an upwards force from the booster of the rocket. At this point, we don't have any other forces acting, so it's kind of simple in that there's an upwards force, and that's basically it. Okay, now what's going to be the magnitude of the acceleration? Well, acceleration is proportional to force, so the greater the upwards force, the greater the initial acceleration is going to be. Okay, so we have a large upwards acceleration at first. Now on the velocity time graph, we can see this. We have this large upwards acceleration here at this point. Okay, now, as the rocket gets higher up into the air, what's going to happen is that it's accelerating, but as it's accelerating, air resistance starts to increase. Now remember from falling objects, when objects are falling through the air, again, as speed increases, air resistance increases. This is now an object that's moving upwards instead. So what's going to happen here? Air resistance increases, and so the resultant force is going to get less. We still have the same magnitude of upwards force as we had before, but now in the downwards direction, we're also going to get a force because of air resistance, and so the resultant force is less. If the resultant force is less, again remember, force is proportional to acceleration, so therefore the acceleration is going to get less. And so our velocity time graph we can see here is curving because the acceleration is getting less and less. Now eventually what's going to happen is the air resistance will be equal to the upwards force, so it's effectively reaching its top speed, kind of like a car trying to reach its top speed. Air resistance is now equal to upwards force, and so the resultant force is zero. Now that doesn't mean that the rocket stops. It means that now it continues at a constant velocity, which is why the velocity time graph is horizontal here. Force is proportional to acceleration. Acceleration is zero because resultant force is zero. Terminal velocity has now been reached. So the rocket's reached its maximum speed. Now, what about if the rocket runs out of fuel? Well, beforehand, when it was going a constant velocity, we had upwards thrust countering air resistance downwards. The forces were balanced, or there was no resultant force. But if it runs out of fuel, then the upwards force is going to cease. It's going to stop. But it's going the speed that it was still, and so we still have air resistance acting downwards. So air resistance is going to be non-zero, acting downwards, whereas thrust upwards is zero. So now we have a resultant force downwards. Now, the rocket was going a certain speed. If it now has a resultant force downwards, it's now going to decelerate. So it decelerates until it sort of comes to a stop.